All right, so moving on to plates. Um, Alfred Wegener, about I think it was a 1920s, he developed this thing called continental drift. And he said that all of the continents that we now know as continents were actually all together, and this was called Pangea. It was like this about 200 million years ago. And then, for some reason, the continents broke up and we get the continents we have now. Okay? The problem with Wagner was that he couldn't explain why they broke up, just the fact that they did. So this was his ideas. Not only did it look like the pieces fit together, I mean, look at Africa and South America there, they kind of look like they fit together, right? But he was able to find fossils, a fossil of this guy on Africa and on South America. And so people were like, oh, okay, that's interesting. But his critics were going, well, it looks like a fish animal, so it just swam across the ocean. Yeah, except this was a freshwater animal. So that'd be like opening up your front door and seeing a kangaroo and not being phased at all. Right? Kangaroos don't happen here in North America. They happen in Australia. So if we suddenly had a kangaroo, we'd think something was weird. This guy, there's a picture of him. He's called a Mesosaurus. And then they also found, and again, I'm not liking this video, but he also found fossils of this tree, or bush, whatever you want to call it, and on Africa and South America. It's like, well, how'd that tree get there? And so his critics are, well, it's the wind blew it over. Uh-huh. Sure it did. Maybe it built itself a raft and traveled across the ocean. I don't know. Now, the other one that the critics had a hard time putting down is the rocks. Okay, rocks do not float across the ocean. They do not blow across the ocean. They do not swim across the ocean. Yet, if you look at the Appalachian Mountains in North America and the mountains in Greenland, they line up with the mountains in Europe and the mountains in Africa. What? How's that possible? Some more evidence that this was actually happening. The continents were moving. So another piece of evidence he found was actually glaciers. Not glaciers themselves, but evidence of glaciers. He found evidence of glaciers in places where you normally think, wow, yeah, well, that has a glacier, like India and Africa and South America, all the cold places on the planet, right? Yeah, not quite. So he found evidence of glaciers, ice glaciers, in those places, which led him to believe that not only were all of the continents together, they were also down towards the pole, the South Pole. So Antarctica, its glacier was so big it covered Africa and India and South America. Now, because he was ridiculed so heavily, his idea was called continental drift, but it kind of fell by the wayside. Now, there were some people that jumped on this bandwagon and they're like, well, let us find out a little bit more. And so they did. And in 1968, they were able to explain why and, in fact, that Wagner was right. The plates were actually moving. And they called this plate tectonics. So in the world of science, plate tectonics is actually really, really young. 1968, 40, coming up to 50 years old now? That's it. So in order to understand plate tectonics, you have to look at what the plates are made out of. The crust. Okay, and the crust is the thin part of the Earth. You kind of saw that picture before where it had the inner core, the outer core, the mantle, and then this thin layer that we call the crust. That's what we live on. There's two types of crust, continental and oceanic. Continental is actually the oldest crust. We can date some of those rocks back to 4 billion years ago. That's incredible. The continental crust is actually the thickest, right? 22 miles on average, or up to 40 miles, like when you're talking about mountains and whatnot. However, it is light, and I know you went outside and you picked up a rock and you're like, this is not light, you're crazy, lady. Well, comparatively it is light. Okay, and it's heterogeneous. The rocks we have here in Tampa are different than even the rocks we have down in Miami or the rocks we have up in Alaska. Now, the oceanic crust is actually quite young, less than 180 million years old. So we went from 4 billion to less than 200 million years old. And the oceanic crust is thinner. It's only 5 miles. So we went from 22 miles to 5. And it's homogeneous. It's all the same stuff called basalt. It's black, blah kind of rock, actually. Now, here's the kicker. It's heavier. It's denser than the continental crust. So the entire Earth is broken up into different plates. Now there's a lot of different plates, but there's major plates. And the 7 major plates are the Pacific Plate, the North American Plate, the South American Plate, the African Plate, the Eurasian Plate, the Australian Plate, and the Antarctic Plate. And as you can kind of tell, well, North America is on the North American Plate. South America is on the South American Plate. Africa, Eurasia. So the continents are kind of named, or the plates are kind of named via the continents, except for the Pacific. That's just the Pacific Ocean, so that's how that one got named. Now, because the plates are moving, there's different boundaries in between the plates. Okay, there's 3 main types, and we'll talk about them. But basically, it's because they have to interact somehow, some way. So the first type is a divergent boundary. This one's kind of simple. You got 2 plates that are moving away from each other. They are diverging from each other. Okay, so that's why we call it a divergent boundary. Now it does create a gap, and so we get hot mantle coming up to fill the gap. Okay, and at these plates we get little ridges because the mantle comes up and kind of leaves like a levee or a ridge there. This is where new crust forms, and these ridges are interesting because they cover 20% of the Earth. Think about that. The continents themselves, the land, only cover 30% of the Earth. And these cover 20% of the Earth. There's almost as much ridge as there is land. Now, a lot of people think that, oh, well, these only happen in the ocean because the most famous one is the Mid-Atlantic Ridge. But that's not true. They actually do occur on land. When they occur on land, we call them rift valleys. This is actually, the Red Sea is a rift valley. It was together, and then divergent boundary was there. It started to move apart, and that's when the water filled in. Okay. Another thing we call it is seafloor spreading. Now, this is exactly what you think. The seafloors are spreading apart, divergent boundaries, right? And on average, it's about 2 centimeters per year. So, if divergent boundaries have the plates diverging away from each other and constantly filling up the gap and creating new crust, the Earth must be getting bigger, right? No, there's 3 different types of boundaries, right? I know I've only covered the one, but if one is constantly creating crust, the other one has to be destroying crust. So the other one is called the convergent boundaries. It's basically when 2 plates collide or converge, right? They're moving together. And what happens is one slides underneath the other one. So in this picture, again, that I'm covering up, you can see it subducting, we call it subducting, or going underneath the other piece of crust. So with the convergent boundaries, we create what's called a subduction zone. The denser crust is going to sink. And depending on how dense it is, it will sink faster. All right, and by that I mean the angle. So if it sinks, if it's super dense, and it will sink straight down, almost like 90 degrees. Okay, and there's not going to be a lot of friction between the two. There's still going to be some, but not a lot. So you're not going to have a lot of scraping. But if it's not quite as dense and it's just forcing itself to subduct, then it's going to create a lot of scraping and a lot more earthquakes and a lot more other stuff. So there's actually different types of convergent boundaries. One type is ocean continent. Okay, and well, the continent, like we had said, it's lighter, so it's going to float. The ocean, on the other hand, is denser, so it will sink. So the ocean's going to subduct. Here we get a trench. You can see the trench kind of forming in that picture. You can also kind of see, but I'm covering it up. There's a little bit of melting because ocean water also subducts too, and that acts as a catalyst to melt the crust underneath. So it's creating kind of a hot spot or a melting. It's coming up, and you can see it's creating volcanoes. We call these continental volcanic arcs. Ocean-ocean convergence work the same way, except it's two ocean plates colliding. And so the denser one is going to sink. And it's going to sink with water, it's going to melt. In the case of the ocean continent, it may or may not create a volcano given how thick the continental crust is. But the oceanic crust is a lot thicker, so it will always create a volcano. And so you get patches or lines of volcanoes. And so these are the Virgin Islands, Japan, Indonesia, Alaskan Peninsula. All this is a ocean-ocean convergent boundary. So here's pictures of the Virgin Islands, and you can see how they've got lines, a linear feature of volcanoes. The last kind of convergent boundary is continent-continent. And continent-continent, both of these are light. Both of these or neither of these want to sink. So instead, what happens is both of them go up. And they create mountains. There's no partial melting because not much is subducting. You can kind of see in the pictures there's a little tiny bit subducting, but most of it is going up, creating faults and folds and mountains. And these are considered the most spectacular mountains on Earth. The Himalayas, the Alps are all considered convergent or continent boundaries. And the last type of plate boundary is the transform plate boundary. The most famous transform plate boundary is actually the San Andreas Fault. Right? And so what this is, they're not creating new crust. They're not destroying old crust. They're basically just sliding past each other. And well, when they're sliding, there's friction, so you get a lot of earthquakes. But you don't get a trench, you don't get volcanoes, you don't get mountains, it's just earthquakes. Alright, so now, what is actually the cause of this plate tectonics? This is what Alfred Wegener couldn't figure out. Well, we think it's the heat of the Earth. The Earth's internal heat is actually causing the plates to move. So the heat from inside is causing convection in the mantle. And there's two different theories on how this convection is working. Alright, so just like convection with the atmosphere, convection inside the mantle. And again, I'm blocking one of the pictures. But one of them, the top one, is called whole mantle convection. They think that the convection starts at the top of the core, right? So the core is super hot, it's heating up the mantle is rising, convection, hot rises, and then the cool part next to the crust is sinking. Or there's another theory, it's called the layer cake, where there's two subduction zones. And so the core is heating up one, and it's causing a convection zone, and then the top part also has a different convection zone. There hasn't been any evidence to support either one, so we're not entirely. So now that we've talked about the Earth's plates, you're going to wish you lived on the moon. Because the moon plates, nope, no plates, no convection, nothing going on in the mantle, no plates actually moving, nothing happening, it's just a solid rock